Okay, so good afternoon, everybody, to this third lecture in fluid mechanics. Today we will have another 3 hours talking about mainly the vorticity equation, actually, for today. But as usual, I would like to start with a summary of what we did last time, and then we will kind of gradually go to new examples. Today, as I said, we will first start to look at one new term that we have in the vorticity equation, the vortex stretching and tilting term. And then we will look at two examples where we can actually use the vorticity equation to get some nice results that can be useful later on. So, but as I said, we would like to start with just looking at a summary of what we did last time. And that's essentially here on the slides. So the first thing that we talked about actually was not just last time, it was also the time before. We talked about the Reynolds number, but because this is so important, it may not actually matter if we just mention that again. The Reynolds number for a specific problem can be defined in the following way, namely that you take a characteristic length scale, a characteristic velocity scale, and you divide it by the viscosity. And this gives you a non-dimensional number, which in the end is an estimate of the ratio of the inertial forces to the viscous forces. So high Reynolds number means that you have a lot of inertia. Low Reynolds number means you have a lot of viscosity in the problem. So if you look here at how this is described, so you take a velocity scale, a length scale, and a viscosity scale. So for instance, for Couette flow, we have defined it in this way. In a Poiseuille flow, for instance, you can take the centerline velocity, or you can take the bulk velocity, some relevant velocity scale, and then you take the distance between the plates or the half width, something like that. Based on the Reynolds number, we could then also calculate the skin friction coefficient, which is nothing else than a normalized wall shear stress. So you normalize the wall shear stress, which obviously, because of, as the name says, is a stress. So you need to normalize it with another stress. And here you just take the pressure, which is the dynamic pressure. So you have another velocity scale in here, but you normalize the wall shear, the wall shear stress like that. So you get the skin friction coefficient. And then what we saw is very similar to the Moody diagram. You have then behavior like this in the laminar flow, very typical that you get a behavior of the skin friction, which is proportional to 1 over the Reynolds number. And then once the flow has become turbulent, you have a behavior which first, in a way that the skin friction at a specific transition location or transitional Reynolds number will jump up a little bit. So you'll have higher friction, but then it will decay again, but at a slightly lower rate. So for instance, for Couette, I guess Reynolds to the minus 0.2 is a reasonable estimate. So this is what we talked about, skin friction. Then we moved on to one of the most important examples in fluid mechanics, that is the Poiseuille flow or channel flow. So we talked a little bit about the plane Poiseuille flow and also the circular Poiseuille flows, pipe flow. And essentially the result that we got was like this, that we obtained the velocity profile as a function of the vertical distance y, so u as a function of y. And we realized that for both channel flow and pipe flow, actually for pipe flow, we didn't do really the derivation, this will come later, but we realized that the shape is essentially a parabola, meaning that there is a square somewhere in the formula. And if you now call this term in the beginning to be u centerline, so the centerline velocity, the maximum velocity in the middle, it's actually a very simple formula that you get. It's just u centerline times 1 minus y divided by b squared. So you get kind of a shape, something like this. Yeah, so we talked about the Poiseuille flow, and then at the very end, we started to introduce also the vorticity equation. So we said that sometimes it's not so useful to only work with the so-called primitive variables, so the velocity and the pressure, but rather at times you would like to maybe use something else. The vorticity is one of those quantities. We define the vorticity, omega, which is a vector, as the curl of the velocity field. So the nabla cross u. And then we could formulate an equation for the vorticity, which is the so-called vorticity transport equation, which is here equation number 2 in the notation from last time. And inside this vorticity transport equation, we could identify a number of familiar terms. So we had the first 2 terms are the material derivative of the vorticity. So we can say that this is the convected vorticity of a fluid particle. Then we had the viscous term here at the other end, which is essentially the vorticity diffusion, which looks very similar as it would look for the velocity, just the viscosity times the second derivative of the vorticity. But then we found a new term here, which we haven't really talked about, omega dot nabla times u. And this term is a little bit, it's a slightly annoying term. Well, we will see how annoying it is, but it's a new term at least, which we don't really know what it is. But at the same time, we were able to eliminate the pressure from the equations. So there is no pressure in the vorticity equations anymore, which of course is a good thing. At the expense, of course, to having this new term, which we need to understand, and also at the expense of needing to specify boundary conditions for the vorticity. But typically you don't have vorticity boundary conditions. You don't know the gradient of the velocity at the wall. You know the velocity, which may be kind of a no-slip boundary condition, but you would not know the vorticity at the wall. So it's not always clear what is easier, but for kind of big unbounded domains, probably the vorticity equation is a good alternative. So what we then also did last time was to look at one example, the channel flow, where we could identify the vorticity as omega z being minus du dy, which then corresponded to 2 times ucl times y divided by b. So we realized that the vorticity is actually varying linearly throughout the channel. Then the last thing that we also talked about was that we can consider the vorticity as being a measure of a local rotation of fluid particles. And there is actually a very easy relation of the vorticity and the angular velocity, which essentially comes from the velocity gradient tensor. And the relation is simple, it's linear with a factor of 2. So omega, the vorticity, is 2 times the big omega, the angular velocity. So this factor of 2 it comes from the definition of the vorticity, and people have chosen to have it in that way. Okay, so this was what we did last time. Do you have any questions or any comments to the topic from last time? Okay. Well, then I guess we can directly go on to the new material. As I said, today we will start with trying to understand this one additional term that appears in the vorticity transport equation, and then we will look at 2 examples. So the term that we need to understand is this one here. I just make a cross, and so let's say we need to understand this term, which looks like omega dot nabla times u. So this is the term that we somehow need to understand what it does and how it affects the vorticity, so that we get an idea of what the overall action of the equation is. So let's just do a very simplified equation. Let's assume that we just have the vorticity transport and this term, but no diffusion. So the viscosity would be 0. So let's just consider a term like this, an equation like this. d omega dt is omega cross nabla times u. So this is the equation that we would like to look at. It's the inviscid vorticity transport equation. Now, to make things a little bit easier, we take, for instance, we look at just one component of that, and we can take omega 2 without loss of generality. We could look at any of those terms. I just take the second row, so the middle row of this equation, and we try to analyze what's happening there. So if I write now the equation for this omega 2, so it's d omega 2 dt, and this, this we can write out now with the, or we on the left side, on the right side, we can now write out what this would correspond to, and that is omega 1 times du2 dx1. That's the first point, the first term. And the second one would be omega 2 times du2 dx2 plus omega 3 times du2 dx3. So now we have just looked at the middle row for omega 2, and what I've written here is the material change of omega 2 given by this additional term. Now, to make things a little bit easier, we can of course associate that x1, this would be x, x2 is the y direction, and x3 obviously is the z direction, and this u2 would be the v component. So let's now try to illustrate what this actually means. So I will consider two situations. I will draw two coordinate systems here. So this is one, and then I have a second one here. So this would be an x direction, this would be the y direction, this would be the z direction. As I just said, this is x1, this is x2, this is x3. So again, x, y, and z. And now let's consider two different situations. The first situation is kind of the middle term, which I would like to illustrate on that side here. And the last term I would like to illustrate in this coordinate system. Okay, so for the middle term, what do I really have? So I have omega 2 times du2 dx2. So that means I have some omega 2 which is multiplied by du2 dx2. So that means here I have some sort of, if I illustrate it here as kind of a sausage somehow, this would be a vorticity omega 2 that I may have in my flow in my flow domain. So this is the omega 2 that I have here. And now this one would be changed by the action of du2 dx2. Well, what is du2 dx2? Well, if we now introduce and say, okay, this length here maybe has a length of dy, then I can say that du2 dx2 times dy, so the change of the velocity in the u2 direction, which is the v direction, which is actually is the velocity in this direction, times this length, this would actually lead to a change in the corresponding vorticity. So that means I can essentially see that the action of this term would be to stretch or to prolong or make this vortex element a little bit longer and a little bit longer by this amount here. So that means if I have a velocity along the vortex, I would have this one to be larger than 0, as in this sketch. So, or to write it differently, if du2 dx2 or dv dy is larger than 0 in this situation, then this means that actually my omega 2 would increase. Omega 2 divided by dt would be larger than 0 if I have already this red vorticity present. So therefore, what happens here on the diagonal of this term, or the middle term here, that is something that is called vortex stretching. So this would be called vortex stretching, because I have a velocity gradient in the direction of the vortex, which would increase the amplitude of this vortex. So that is what's happening with the term in the middle here. Now let's look at the last term, and we try to see what's happening there. So we do the same analysis. So we say, okay, now we're actually needing to look at omega 3. Omega 3 would then be, and if I'm drawing it as a sausage, would perhaps be something like that. And I can associate a certain length to that. In this case, it would be a length of dz. But now the velocity that is relevant to change this vorticity is actually dv dz. So that means I need to have a velocity gradient of the v velocity as a function of z. So the action of this term would actually be, so that would be the velocity, something like that. The action would be to kind of tilt my vortex. So the vortex was straight before, but now I have this velocity gradient, so it will tilt this vortex. And how much does it tilt? Well, in this case, I would have du2 dx3 times dz. So this here would now correspond to the tilting velocity that I have. Whereas here it was the stretching velocity on the left side. Here it would be the tilting velocity. And of course, now the consequence of this is that after the tilting, so for the green line, I would then have actually some omega 2 vorticity being generated, because I have kind of tilted this vortex, so I have a projection on the in the y direction coming from this vortex. So in this case, this would be possible if du2 dx3 is larger than 0, so that if we have this gradient, then I would get d omega 3 dt being larger than 0. And as I was saying, this essentially corresponds to the fact that I'm tilting a vortex. That's why this term is called vortex tilting. And of course, now it's easy to understand as well that the first term here would do the same as the third term, just in the x direction, where you have du2 dx. So that would kind of be the same thing if you were to do it in this direction. So therefore, the first term and the third term, they essentially do the same thing. They are responsible to vortex tilting, and the one in the middle is responsible for the stretching. All of them, they lead to a change of omega 2, either by stretching, as I was saying. So if you have already vorticity there, it will be stretched if the velocity gradient is aligned with it. And if the vorticity is looking in another direction, it would be tilted into omega 2. So therefore, this term here is called the vortex stretching. Oops, vortex stretching or vortex tilting term. And because this depends on what direction it is, you can essentially say that the diagonal would correspond to the vortex stretching, and the off-diagonal terms to a vortex tilting. But all of them, they contribute to an increase of vorticity in a specific direction. So that term actually serves as a source or a sink term in the vorticity transport equation. So they may lead to an increase of vorticity. There is one important point here, and I guess that point will then be made by Ramis in the second part of this course. If we consider a two-dimensional flow, then we actually have the situation that this term, this vortex stretching or vortex tilting term, is always 0. And the reason for that is because the vorticity and the velocity gradient, they're always orthogonal to each other. So the dot product between omega and the vorticity, the velocity gradient is always 0. So that means in 2D, there is no vortex stretching or vortex tilting. Or vortex tilting is 0. And why I said that Ramis will talk about that? Well, vortex stretching and tilting is, of course, an integral part of turbulence or a turbulent flow, where we say that one of the main characteristics is that the turbulence is vertical. In 2D, this is not really possible. So therefore, it is questionable whether you would like to call that then a turbulent flow. Okay, so this here is an explanation of this additional term that we have, which replaces, in some sense, the presence of the pressure in the vorticity transport equation. You probably should take a minute and try to understand these sketches that I made here to fully grasp the concept about what stretching means. If you have essentially making, the velocity oriented in such a way that you would make a vortex line longer. In that case, you would get vortex stretching. So this, in this case, you make a vortex element in the y direction longer if you have du2 or dv dy being non-zero. So then you stretch it, or in the other case, when you tilt it, then you also increase the vorticity. Okay. So this was about this term. Now I would like to move to two examples where we can use the vorticity transport equation in an effort to understand how we can use it. So I'd like to call this practical examples. And it's two examples that I would like to make. The first one is something that I call unidirectional flows in a steady case. So, well, I can maybe let's do like this. We call it steady unidirectional flows. So move this. So steady unidirectional flows. So that could mean, for instance, a pipe flow would be a steady unidirectional flow. Well, actually, we can maybe directly start there. What do I mean with unidirectional flows? Well, I mean, it's the flow that only goes in one direction. And now again, without loss of generality, I can assume that this direction in which the flow is going is aligned with one axis of the coordinate system, and I can take, for instance, the z direction, which is what we typically do. So if we draw a coordinate system, something like this, if this is my coordinate system, then unidirectional flow would mean that all the velocity vectors, irrespective of where they are, they would all show in or point in the x direction. So that means then that my velocity vector could be written as some variable, some scalar variable, which is a function of x and y times the unit vector in the z direction. So this here, this is what I would call a unidirectional flow. And also, since I'm not writing a time dependence here, I would also call it to be a steady flow. Now, I do not specify here what the shape of this pipe or channel or duct or whatever it is. It could be, for instance, I'm trying to just show maybe, well, it could be like a star, something like this. So this would be a perfectly valid geometry in which I have unidirectional flow, and then the flow would just kind of come out of this star, for instance, star-shaped pipe, for instance. So the goal for now is to calculate the flow field inside such a geometry. Just to be very clear, I just write it down again. Unidirectional means only one component of the velocity is left. Only one component of the velocity vector, sorry, is non-zero. And as I said, I can align that direction with whatever coordinate direction I want. I just choose here the z direction, so that means that my velocity field is only a function of x and y. Okay, let's now go on and let's see what we can calculate based on the equations that we have introduced so far. So we can start with the continuity equation. Well, we know how this looks. du dx plus dv dy plus dw dz is 0. So this is the continuity equation. Now I can get my green pen and I can essentially remove most of the terms here. Why can I remove them? Well, I have said it's a unidirectional flow, so that means that actually u and v, they don't exist. It's only the w component that is present. So that means u and v are actually 0 in this case. And of course, this means that we only have dw dz being 0 left. And what this means is that w has no dependence on z. So that means whatever cross-section I look at of my pipe, it has the same velocity. There is no dependence of the z direction in there. And of course, that's already an important result. So I know that there will be no derivatives in that. Now, the next step would be to actually look at the vorticity equation, as we kind of said in the beginning. That's what we would like to look at. So the vorticity, as we defined it, is nabla cross u. So the curl of the velocity And because the velocity is a little bit simpler here, as we have written here, it's only one component, I can directly write that this would actually be dw dy in the x direction would be minus dw dx in the y direction and 0 in the z direction. All the other terms which involve u and v, they are 0 because we have just realized that u and v is actually 0. Maybe I should be kind of explicit here. Actually, u and v, so the velocity in the x and the velocity in the y direction, they're 0. It's only w that is left. Okay, so this here is my vorticity, and of course this component would be the vorticity in the x direction, and this would be the vorticity in the y direction, like this. Okay, so now we know that the vorticity is a little bit simpler, so we can go to our vorticity transport equation, which I just write down. So we have dw dt, then we have the convective term, u nabla times the vorticity. Then I have this vortex stretching term that we just talked about, omega times nabla times u. And then we have the viscous term nu times nabla squared omega. And this should be 0. Now, again, I can take my green pen, and now since we have already reduced the vorticity quite a bit, and we know a little bit more about what velocity components are actually present and which ones not, well, we can take away most of the terms. So the first one goes away because we said that we talked about a steady problem. This one, the nonlinear or the advection term also goes away because actually it turns out that the velocity u will be orthogonal to the changes of omega. The third term, the vortex stretching term, goes away for similar reasons because omega is in fact orthogonal to the changes of u. So what is left is actually only this term here, the viscous term. And that means that for this particular case, so the case of a unidirectional flow, the only thing that is left is actually nabla squared times w being 0. Now, of course, I could divide by the viscosity because it's a scalar. So this here is the equation that I need to solve. And once I have solved this, then I have solved the problem essentially. So we can say we have a Laplace equation for the vorticity. So the vorticity needs to fulfill Laplace being 0. Of course, that doesn't help so much for us now when our question is to calculate this w, because we in the end we're not so interested in the vorticity. We would actually much more like to calculate w, so that the velocity in this streamwise or axial direction. So we kind of need to find a way of working a little bit with the vorticity equation, or this whatever is left, the Laplace equation, to actually get a little bit better understanding of what actually w is. But still, this is what the vorticity transport equation gives us. So whenever we can solve this equation, we have a vorticity, and then we could use the vorticity to calculate the velocity. But let's try to do that now. we just start by writing out what the Laplace equation would actually mean. Well, it's two components. It's a vector equation, so we have two components. Actually, we would have three components, but the third component is not very interesting because that's the vorticity in the z direction, which is 0. So we have two components. So we have d squared. Now I'm taking omega x dx squared plus d squared omega y dy squared, and this should be 0. So keep in mind, I'm taking now the omega x and the omega y. That's these two terms. So that's the first line, and then the second line. Of course, I did that wrong. This one should of course be an x. So that's the first row, and the second row would be d squared omega y dx squared plus d squared omega y dy squared, and this is also 0. So now the next step would be to actually take the definition of omega x and of omega y in terms of the velocity w. Now you need to be a little bit careful with not mixing w and omega, which is a bit difficult when I'm doing that with handwritten notes. But the w here would be the velocity, and the omega here is the vorticity component. So what I can write here is by just plugging in the definition of omega x and omega y into these equations, and then actually reordering the order of the derivative, what I will get is d dy of d squared omega, d squared w dx squared plus d squared w divided by dy squared. As I was saying here, I was reordering the derivatives. So that means I used the following theorem. So d dx of d squared dy squared, for instance, that's the same as d dy of d dx times d dy. So I mean, I can switch the order of taking derivatives, and this is also called, as you all know, the equality of mixed partials. That's the name in English, mixed partials, or there is it's also called the theorem of Schwarz. But at the end of the day, it just means that you can switch the order of derivatives, as we all know. But this I have applied here. So for instance, for the first term here, I have this derivative of y I have taken out. So I have only the x derivatives, and for the second one, I have the x. For the second term, I have omega x again, the y derivative that I have taken out, and then it's just the y derivatives left. I can also do the same operation. So shouldn't it only be y in the bracket and not y squared? Y in the bracket and not y squared, y in the bracket. Well, I mean, okay, well, let's do like this. Let's do this here in more detail. So we have d squared dx squared times omega x. What was omega x? It's dw dy plus d squared dy squared times the same, dw dy, right? And this should be 0. And what I did now is I took the derivative d dy I took out, and then I have left the d squared w dx squared for the first one. I took this one out, and for the second one, actually, well, doesn't really matter, but I can view it as I take this one out if I want, and then I get obviously what is left, which is d squared w dy squared. Okay. Good. Okay.
Professor.
Yeah.
I have a question. Why in the first and the second equation we didn't put d square omega x on the z square?
You mean this one?
Yes. Yes.
Because this is 0, because there is no change in the z direction.
Oh, okay. Yes.
Well, we kind of got it. We got it here for the velocity, but that also means that, of course, the vorticity would also not change in z. I mean, if the velocity doesn't change, then also the vorticity would not change. I mean, it's essentially fully developed in the z direction. So that's why, I mean, you're right. In principle, there should be the set. Maybe I just write it here, that essentially at the end, this would mean that ddz would be 0, except for the pressure. You know, it's the same thing as for a pressure-driven flow. You would still have a pressure gradient, but fortunately we don't care here because we look at the vorticity. But the set dependence would be gone. Okay. But anyway, now we're at this stage, and I think now you believe me if I just write the same. In this particular case, I would get minus ddx, and then in the brackets, I would get the same, d squared w dx squared plus d squared w dy squared, like this. Okay, and now this is actually interesting. Because now I have, well, first of all, this quantity that is in the brackets here, this is actually something that we can write down. This is just, the second, it's Laplace of w. Laplace of w would just be d squared w dx squared plus d squared w dy squared. But now you see that the y derivative of this Laplace and the x derivative of this Laplace, both of them are 0. And of course that means, well, if it's only a function of x and y and both derivatives, partial derivatives are 0, it means it's constant. There's no other way. So what this actually means is that Laplace of w is a constant. And this constant, just for naming it in some way, I can name it with the letter k, or the variable k. So this now is a Poisson equation for the velocity w. So before we had, so up here we had a Laplace equation for the vorticity omega. And then we could see that this actually corresponds to a Poisson equation for the velocity w. So if we now want to solve for the velocity field for the velocity w, so if we kind of want to know what this w here is, w of x and y, then I just need to solve a Poisson equation with a specific k. So it's a Poisson equation, it's not Laplace. So that means that there may be a non-zero value. And I guess we will spend now the next half hour after the break to understanding what this value of k is. But I guess most of you can already kind of imagine that this k probably has something to do with a pressure gradient that I would apply to the flow. But still, we have now gone from a Laplace equation to a Poisson equation for the velocity, and that's already a very important step that we could take. So the next question, which we then address after the break, is the question: what is this k? Can we calculate that k in any way? Okay, with this, I would like to stop the recording for now.